saw the analysis of LHCb for the search of dark photons decaying into a pair of muon particles. Better? Sorry. And we saw that the analysis was performed by dividing the data sample into two subsamples depending on the lifetime of the dark photon. So basically there were two data samples, one where it was possible to define a displaced vertex for these events, and the other were considered prompt, so decay immediately after the generation of a dark photon. We saw the analysis for the prompt case and the result, and we saw also which are the main backgrounds which are bound related to the misidentification of particles as muons within the detectors. And now I want to move to the long-lived analysis, and I want to mention and to discuss in particular about the main background for this search, which I think is very interesting, because since you are asking for this particle to have a displaced vertex, basically this request helps to reduce a lot all the backgrounds which are encountered in the prompt analysis. But you have other kinds of backgrounds. For example, this one is due to the fact that you may have a photon produced in the primary vertex that cross the layers of the Velo detector, which I remind you is the most inner part of the tracking system, and then it can convert into a pair of muons, and then you may think that those muons were actually coming from the decay of a dark photon which had traveled up to the tracking detectors and then had decayed. This is very complicated background to treat, and the strategy that LHCb adopted to reduce it up to being negligible is very interesting, because what they did was basically to build a map, a three-dimensional map of what is the material budget of the inner part of the tracking detector. And they did it using other data sets where, when they selected the hadrons produced inside this detector. So reconstructing the vertexes of the origin of these hadrons, they were able to understand where they were produced, and therefore to map in a 3D scan what is the material budget of the Velo detector. And here you have the result. This is the profile projection of the 3D map they obtain, and as you can see how precise it is. Here is the scale, and you can see that it reproduces almost perfectly the detector. And then they use this information to define the probability that one of the dimuon events they had labeled as displaced vertices was actually coming from the interaction of a photon inside the Velo detector. And in this way, they optimized a cut on this probability, and they were able to reduce this background up to negligible levels. So I think this is very, very interesting, and also proves how these vertex detectors are precise in defining the vertex of the particles.
Can you explain a little bit more the image we are seeing, because I am confused about the detector?
This one?
Yeah.
Okay, so this is a photograph of the inner part of the first, let me come to the sketch of the detector here, of the most inner part of the tracking system, which is basically surrounding the interaction point. So you have all these layers of silicons that is just like a CCD of a camera phone that register the passages of particles and give you the information of where was passed the particle had passed, so what was the trajectory. And it is a sort of series of layers of these silicon strips, sorry, wrong way, that register the passage of a particle. And here you have one of the two halves in which the detector is divided, because you have to imagine you are surrounding the interaction point from where the two beams come, and here you have the two halves of the detector. This is the bottom one, and then you have another one, which is not in the picture now. Now it was just for showing in the picture. But here, for example, in this profile, which has been built using the reconstructed vertices from hadrons produced inside this material, you have both halves. So this is the profile of what you're seeing here, basically.
Okay, thank you.
Okay, so about the analysis of the displaced vertex, there are some striking differences compared to the prompt search. In particular, you can see that the range of masses explored is much smaller. On the lower side, this mass range is limited at 214 MeVs, and this is the same as in the prompt case, simply due to the fact that we are searching dark photon decays to 2 muon particles, and if a mass goes below 2 muon particles, you cannot decay into those particles. But on the larger mass size, the limit that you have here is due to the fact that if the dark photon become more massive than 350 MeV, then his average gamma factor, due to its large mass, is too low to allow it to travel enough to be detected as a displaced vertex in the detector. So this is a very limited in range search compared to the prompt analysis. But on the other side, given the fact that you are using the information from the aspect that the vertex is detached from the primary vertex, you can reduce backgrounds, and also you can have larger efficiency, releasing some cuts in the analysis. So as in the case of prompt decay, the data sample were divided into bins depending on the invariant mass measured, but now they were divided in 2 dimensions, so in bins on the invariant mass, but also on the lifetime. And each one of these bins was fitted with probability density functions that included the information about the dark photon production, all the background considered with all the uncertainties. And this allowed to obtain some values for the parameter epsilon square and some limits to place in the dark photon scenario. I say some limit because there was no observed significance for the discovery of a dark photon. That is to say, the measurement was compatible with hypothesis of no dark photon at all. So this is the result in blue about your exclusion limits. This is mass of the prime, and this is epsilon square. And so these are the two spots that you could see in the large parameter space that I showed before, and that you can see again here. So this is the final picture of the result of analysis of LHCb. This is the exclusion limit derived from the prompt decay search, and these are the two spots limited by the display detached vertex search. Now, before moving on, I just want to mention that LHCb is not only the only collider who placed important limits in this scenario. There are other cases. In particular, I just want to show here the exclusion limit from CMS, also another experiment at CERN, and also the results from Babar, that can you see here, which was an older collider experiment at SLAC in the US, which was instead an E plus E minus collider. So you had two beams of electron and positron colliding, and they searched as their final state the annihilation of electrons and positrons into one photon and the dark photon, where the dark photon after decays into an electron-positron pair. So at the end of the day, your final state for Babar was one photon and one electron and one positron. Instead, CMS searched for decay in the muons, as for LHCb, produced by many processes such as Higgs decays. So this is the picture for what regards the collider in the visible.
Because I think that those sky blue regions are LHCb2, and well, that's my question regarding this graph. But also, why don't we increase the mass of the A prime, but decrease the coupling, so that we can have other searches too?
I'm not sure I understood. You mean why do not increase the mass?
Yeah.
What do you mean?
Because you are probing. In your last slide, you said you were probing for, from 214 to 350.
Yes, and this is what you see here. Sorry. Okay.
Yeah. So the question for the range of mass would be, why don't you increase the mass, but maybe decrease the coupling, so that you still have maybe still a long-lived particle?
Oh, I see. Well, it's a trade-off, basically. So on one side, you are limited by the lifetime of the particles, and one side you are limited by the fact that you produce too few particles, not a large number enough to detect them. So it's the fact that these regions are very small is because there you have the really right cocktail of parameters to have a particle that can be at the same time produced in a large enough number and live enough to be detected as a displaced vertex. So that's the reason. This is you have to remember that it is a logarithmic space. So even if here seems really small, the phenomenology of this particle changes a lot between maybe here and here. So here you may have particles with escape the detector, for example. Here particles that cannot be detected as a displaced vertex.
Got it. Thank you.
Okay, so before moving to thin target, I just want to mention that you cannot just you cannot only search for visible decays at colliders, but you can also search for invisible decays. And in that case, you don't have any visible final state that you can tag as the signature of dark photon production, because you have chi particles, so you have not the muons to tag in your analysis. But what you can do in some cases is to use the so-called missing mass technique. So if you have, for example, some interaction between two colliding beams where you have a production of many particles of a standard model and a dark photon which decays invisibly, if you are able to detect and correctly reconstruct all the momenta of these particles, you can just build this quantity, which is the so-called missing mass, and this missing mass is peaked at the mass of the escaped particles. So you can build basically for all these events a spectrum of missing mass and then search for peaks defining, for example, a dark photon. This is complicated, obviously, because you have to measure all the particles produced inside within a collision. And for example, as we saw for LHCb, which is a detector which has no 4π coverage, so it covers only a small portion of the solid angle around the collision. It's really complicated to detect all these particles. But there are some cases where this is possible, and some analyses have been performed. In particular, one case is Babar. which is the experiment that I mentioned before, also for a visible search. It was a collider that was able to set important limits also in the invisible scenario. This is due to the fact, to two main facts. The first one is that, as I said before, is an electron-positron collider. And if you produce dark photon via annihilation of electron-positron collider, you can have a final state where you have a gamma and a dark photon. So you have not many particles to detect if you want to perform your missing mass search, just to detect the single photon that is emitted from this reaction. And the second thing is that, as you can see here, the detector, which I'll describe briefly in a moment, has a barrel shape, and the interaction point is within this barrel. So you have very large angular coverage, and so you can basically be reasonably sure that if you produce something, you will probably detect it. So this was an experiment that was not optimized to search for dark photon. Actually, it was optimized to the physics of the beauty quarks, so meson with the beauty quarks, the Y. In fact, the energy in the center of mass was that of these resonances here that are made of beauty quarks, which is of order of 10 GeV. But still, this was a very good experiment to search for dark photon. The detector has a philosophy which is similar to the collider that we saw. We have the tracking part inside, so I mean all the silicon pixel that detect the passage of particles and give you the information about the momenta and the position of passage. And also you have a calorimeter, which is in this case made of scintillating crystals. It was sodium iodide, and this was enclosed inside a magnet, so you have a magnetic field inside, allowing you to measure the momenta of a particle. So they performed a search for dark photon, and what they did was to basically, as I said, perform a calculation of the missing mass and search for a peak in this spectrum of missing mass. And this is the result, the limit they excluded because they did not find any evidence for dark photon, which you can see for large masses is still the most competitive limit that we have in the dark photon invisible decay scenario. It is interesting to note the shape of this exclusion limit. We saw for LHCb, for example, that the limit is very irregular. This is due to the fact that the invariant mass spectrum was divided in beams depending on the sensitivity of experiment as a fit, and a fit was performed for each of these beams. This was done also for Babar, but due to the resolution of the detector and the mass of the dark photon, which is considerably light with respect to the center of mass energy of the detector, the resolution is such that this here is a single beam of analysis. So Babar was not sensitive to the mass of the dark photon from 1 to 100 GeV. It was a single analysis in all of this missing mass in the spectrum. And this is the reason why this limit here is flat, and also the reason why colliders typically are more well suited to explore for larger masses. This is also the reason why we are built. They are built to create new particles with, in general, large masses with respect to a fixed target experiment. Okay, so we come finally to the end of our this description of collider experiment in this field, and we move to the fixed target experiment. So what we saw is that collider feature important sensitivity in the large mass part, and this is due in particular to the large square root of S they can achieve. That is to say, the energy in the center of mass that a collider can achieve is very large. This is due to the fact that if you have two beams colliding with each energy E beam, the total energy available in the center of mass is obviously 2 times the energy of the beam. While instead, if you have a single beam impinging on a fixed target, that's not more the case. And the square root of S of energy available at center of mass depends, scales at the square root of energy. So it's complicated to produce very massive particles of fixed target experiment. But since now we are thinking of a scenario where the masses of the particles, of dark matter particles, are very small, maybe not necessary to have this large center of mass energy, and it's better to stick with a high intensity experiment to search for rare events instead of a very large energy collider. So this is a bit of a change of paradigm from what is called the energy frontier, so raising the energy of the colliders and the square root of S to build very massive particles, to the so-called intensity frontier, so the luminosity of the experiment, the number of particles on target and interaction that you have. And this is the reason why you can search for these scenarios even with small-scale experiment with fixed target, as we will see from now on. So a typical fixed target experiment searching for light dark matter can be schematized like that. So how do you produce dark matter at a fixed target? Well, dark photon is basically, as we said, a photon from the kinematic point of view. So you can produce it in the same way that you could produce a standard model photon. So for example, from a radiative process that in this case is usually called a Strahlung to recall the Bremsstrahlung process. So you have, for example, an electron beam. It impinges on a thin target. You have this radiative process, so you produce your dark photon. And then, if, for example, you are in the visible decay scenario, this dark photon can decay into a pair of electron and positron. Here, we are assuming electron and positron are not muons, because now we are considering a range of mass which is below 2 mass of muons. So this is the signature for this decay. Here you have some values. For example, for what is the characteristic dimension of the angles of the two electron and positrons, which you can see depends on the energy of the beam. It can be very small, order of milliradians, and also the fact that due to this process in general, you can assume that the dark photon takes most of the energy of the beam in this process. So you end with a dark photon which has almost all the energy of the beam, and then you can try to detect its decay product, both searching from an invariant mass spectrum, as in the case of LHCb, but also searching for a displaced vertex, as in LHCb, but now with a fixed target experiment. And this is the case of the first experiment we are going to talk about, which is HPS, which stands for the heavy photon search experiment. Heavy photon is just another name that was given mainly in the past to the dark photon particle. So this is basically a very compact spectrometer which aims to both detect displaced vertices produced by the decay of dark photons produced in a thin target where electron beam impinges, and also the peak in an invariant mass spectrum from the detection of the two electron and positron inside an electromagnetic calorimeter. The ranges of energy for such experiment are fairly low compared to the collider energy, so we're talking about energies between 2 and 4 GeV. We have a thin tungsten target in this case, where the A' Strahlung reaction occurs. And then you have a silicon vertex tracker and a calorimeter made of lead tungstate, which is an inorganic scintillating material, to detect the displaced vertex and a search for invariant mass peak. So from a point of view of tracking, you can think basically of, from a functioning point of view, what we saw for LHCb. So detectors that, which are able to reconstruct the passage of particle, their position. And since you have a magnet where all this system is enclosed, your particle will curve and you will determine their momentum. So here there are, as I said, the two distinct strategy of search for HPS. The first one, the resonance search. So here this is a simulation, that's not real data. Unfortunately, a simulation where some signal fake was injected. Here is an example of what to expect for a missing, for an invariant mass spectrum, where you have all this flat distribution, which is given by all standard model processes that can result themselves in an electron and a positron inside the calorimeter, because obviously there are many processes that can produce such particles, and this is your very smooth background. And on top of that, if you have a dark photon, you would see it as a very small bump within this distribution. This is, I mean, to be able to be sensitive to such bump, this is very complicated, because you have to control very well all your backgrounds and the stability of the detector. So this is very difficult to achieve low epsilon value. So we can say that the main discovery potential of HPS is the displaced vertex detection. So due to the tracking, you can basically, again, this is simulation again, this is simulation, not real data. You can build a distribution of reconstructed vertex position with respect, for example, to the target. And here is how it is distributed, your standard model background. And if you have some long-lived particles, such as a dark photon, it would distribute like that. You would have a tail that you can analyze with statistical method to define the discovery of a dark photon or put some limits. Before going a bit more into detail about the technology of HPS, I want to say a few words about the laboratory and the accelerator that HPS is making use of, which is the Jefferson National Laboratory at the United States, in Virginia, also called JLab. This is a medium-sized nuclear physics experiment in the US, and it makes use of this CBAF, which is the Continuous Electron Beam Accelerator Facility, which is the accelerator itself. It is not a circular shape, but it's an oval, because it's composed by two parts, which are linear, that accelerate the electron beam, and two curved parts, which just allows for the trajectory to bend and to reach the other linear section. So particles can make several passes within this system, and for each passes, for each turn they complete within the accelerator, they gain 2.2 GeV of energy. They can do it up to 5.5 passes to reach an energy of about 12 GeV. And then these particles are basically distributed to 3 experimental holes at the same time, which can operate simultaneously, where the different experiments of Jefferson Lab are located. So HPS is located in what is called Hall B, which is the central one here. As you can see, these are the rooftops of the hall. And one of the particularities of this beam is that it is basically continuous. So in general, particle beams have a time structure, such as you have bumps. You have moments where you have the passage of particles, then nothing, then another spill of particles, and so on. In that case, due to the very high frequency of operation, the beam is basically continuous. It's like having a continuous current of particle flowing to your experiment. And in the case of HPS, this current is of about 100 nanoamps, so significant current. Also, it is a very high quality beam from the point of view of the shape of the beam, because a particle beam may have a large profile, and in this case the beam spot is very focused in lower than 50 microns vertical acceptance, and also is very stable, so its average position in vertical position is very, very stable, less than 30 microns. I'm talking about a vertical position, which is the one interesting for HPS. And the reason is because the tracking system of HPS has to detect very low angles, which are the aperture angles of the two electron and positron emitted by the dark photon decay. And since this angle, due to the masses and the energies in play, is very low, you have to be able to place the tracking detector, which are these strips here, so we detect the passage of the particles, very close to the beam. And since these are very delicate sensors, you cannot just place them in the beam. You have to be careful and be sure that you can go close up to a certain level, but the particle on the beam don't hit directly the sensor, otherwise they would damage it. And this is possible given the very, very high quality of the beam provided by Jefferson Lab. So, a bit more in particular in detail about the design of this silicon vertex tracker. So it's made by 6 layers. This was the original design. Now they added one more for more resolution, but that does not change the idea. And it has an acceptance which goes down to 15 millirad, which means that you are close up to 0.5 millimeter from the axis of the beam. The detector is split into halves. As I said, you need to get close to the beam, and now what we've done is that the detector has the upper part is lowered towards the beam, and the lower part is raised toward the beam, so to get the most solid angle covering. And you have that resolution for each layer of about 6 microns in the vertical plane. Here I have a picture of this detector, the silicon strip. So this is the active part, basically. And you have also all the electronics that is responsible for the readout and data acquisition and amplification and so on. There are obviously precision actuators to define the position of this detector because you want to be sure, as I said, not to place it inside the beam and to destroy them. And so there is a quite complicated procedure to operate this experiment. So you have to perform scans of the beam profile, then you do the scans with the detector itself, you progressively make them closer to the beam up to the operating position. Here, for example, we have some results from the scan of the beam shape in correspondence of the silicon vertex trackers of HPS. So this is there are some detectors along the beam line that basically measure the distribution of the particle of the beam with respect to the axis of the beam itself. So you have this different detector, which is called beam position monitors, and there are many. This is one of them, which is placed just in front of the XPS experiment, and these are used to understand if the beam quality, the beam tuning is fine enough to proceed with the lowering of the silicon vertex tracker in the correct position. And this is control is performed continuously, because it may be that for some reason the beam steers and changes its direction and hits the silicon vertex. So this control has been done continuously, and to be sure that nothing wrong is going on. Here you can see the resolution, which is the spread of the beam, which is better in the y direction, which is interesting from important from HPS, since, as I said, the silicon vertex come from the top, from the bottom, and this is the y. But still, we are talking about really a small beam spot. And here you have a wide position scan, which is a sub-detector of the HPS silicon vertex detector, which can itself measure the profile of the beam without having to put the silicon itself inside the beam. So it's like a small wire that you pass through the beam, and depending on the number of particles that hit this wire, you see a signal which is larger and lower. So you make some points, and you have a profile, and you can define with if the width of the beam at the position of the SVT layer is good or not for your operation. Okay, so that was for the SVT. We now come to the electromagnetic calorimeter part. So this is important both for the bump hunt search, but also for the trigger. In fact, the trigger to this experiment is given by the electromagnetic calorimeter. So when you see an electron and one positron, so the position of energy into two parts of the calorimeter, you can trigger an event. So how it is produced, how it is designed, the calorimeter. As I said, are lead tungstate crystal, which should be a 4 and not a 0, sorry. And they are divided into two halves on top of the bottom of the beam. This is due also to the fact that, as I said before, you have a magnetic field before, which is bending particles. So you have basically different energy particles bended all throughout this hole here. So you cannot just put crystal there, otherwise the radiation damage would kill them. And it has 442 crystals in total, which a dimension of almost 1 centimeter per 1 centimeter, about 1 centimeter per 1 centimeter, and 16 centimeters long. There is also, which is interesting, a custom LED monitoring system that works as a calibration point for your calorimeter. So as we will see later, what may happen is that due to radiation, due to the high intensity of particles impinging on these crystals, the crystals get damaged. What does this mean? This means that they does not transmit light as good as they were in their origin, as they were new. So you may see lower signal, thinking that it's a lower energy signal, but instead it's just the crystal that is not transmitting light in a good way. So you basically recalibrate this, just impulsing some LED light inside each one of the crystals, and if you trust the LED to be stable during time, you can recalibrate your crystals, your calorimeter, and account for variation due to the transparency of this crystal. Also, there is a cooling system because all the electronics and the acquisition, the light detection amplification have a dependency on temperature. So there is a cooling system that allows the calorimeter to be thermostated at about 0.1 Celsius degree. You have a picture of one of the layers where you have one crystal. You can see here it's transparent. It is how it should be as it is new, so like glass basically. And here you have a measurement of the performance of this detector. So what I mean with this performance, basically the energy resolution. So if an electron impinges on this detector with such an energy, what is the response of your detector, and what is the resolution of this measurement? How it is done? This is done using a particular characteristics of events, which is elastic scatter of electron of a beam inside the target. So you have your 2 GeV, 4 GeV, 1 GeV electron impinging on the target. It can many things can happen. It can also happen that interact elastically with the nuclei of the target, which means that electron changes their momentum, but they don't change their total energy. So the energy is the initial energy of the beam, but the direction is different, so that it hits the calorimeter in different position, and you can use this signal, since you know the energy of the beam, to calibrate your detector to measure the resolution of your detector. If, for example, is a peak of energy measured with an energy beam of about 1.1 GeV. And here, if you repeat these things many times and you perform a fit to these signals at different beam energy, you can evaluate your resolution with respect to the energy. And as you can see, it follows with a shape here, which is typical for electromagnetic calorimeter. Usually the resolution for electromagnetic calorimeters is defined by 3 terms, which are due to different possibilities, different happenings in the process of depositing energy in a calorimeter. So this is a relative resolution, so the sigma E over E, and this is composed by 3 pieces, 3 terms, which has been measured and has been obtained by a fit to this point. And these are the first one, this is called the electronic noise term, so which is a term that goes down with the inverse of the energy, which is due usually to electronic noise in your detector. Then you have a term which goes down as the inverse of the square root of the energy of a beam, which in general is due and attributed to fluctuation in the statistic of a shower, so it may be different number of particles produced, and also statistical fluctuation in the number of photons produced by your light detector, which follows a Poissonian distribution, so it's like it has its own statistic and its own fluctuation. And finally, you have a constant term of the resolution, which is usually attributed to leakage, that is to say that your detector is not fully containing the particle that is impinging on it, and some of this energy is escaping, and sometimes is more, sometimes is less, and this results in contribution to the resolution of the detector. And so these are the numbers fitted for this calorimeter, which is really reasonable for the type of detector and in agreement with the requirements for this experiment. Okay, before moving on, I want to come back to what I said before about the reason why you need LEDs to recalibrate this kind of detector. So this plot here shows for each crystal of the calorimeter the ratio between the amplitude of the signal caused by a light pulse produced by a LED in the crystal before and after 70 hours of exposure to the beam in the nominal operational intensity of HPS. So basically, where you see red, it means that there are fluctuations and the signal from LED is larger after the beam than before, and when you see blue, it means that the signal from the LED is lower after the exposure to the beam. And what you can see here, that the fluctuation around all the calorimeter are quite reasonable. I'm talking about 5 per mil, so nothing relevant here. But there is some region around this hole here of ECAL where already after 70 hours of data taking, you have that the LED signal is lower of a few percent even. This means that the radiation that impinged on these crystals here was so large that in 70 hours reduced the transparency of the crystals. And so you already have an appreciable effect. And this is reasonable that happens around this hole here, because here is basically where the beam passes if it does not interact with the target, so it crosses the target without interaction. So this is interesting. It is something that in such an experiment has to be considered carefully and corrected in the analysis phase. Still one slide on the calorimeter, because as I said, is used in the definition of what is the trigger of the experiment. So you are searching for electron-positron pairs. You know that they are emitted from the decay of a particle. So you are searching for the decay of a particle. So you may define the condition for example, the heating position of the particle in the calorimeters, which are in agreement with the origin of the decay from a dark photon or not. So what is done is that you require energetic cluster, which is to say an ensemble of crystals close to each other that show a significant amount of energy, which is not due to the interaction of an electron or positron, and they has to be displaced horizontally in the opposite direction from the center line of the unbent beam, according to their energies. But obviously, if you have lower energy particles where they cross the magnetic field, they bend more, and so you have to take into account this. And at the end of the day, combining the energy measured and the impact position, and therefore the angle with respect to the center line, you can build online a trigger which is quite efficient and allow you to save only interesting, let's say, events for your search. I did not mention it before, but I think, I mean, maybe it was obvious, but I will say it again. So if you look at this picture with the perspective of the incoming beam before the target, the center of the target is here. But this hole is here, is slightly displaced from the center because we have a magnetic field, and so the majority of the particles, when the beam does not interact in the target, are bent in this location, which is not symmetric with respect to the calorimeter, not with respect to the target. Okay, so what are the main background for this search? All the standard model processes that can result in the same signature for the experiment. So radiative process, so where you have a radiation of a virtual photon which decays into electron and positron. So the signature in that case would be basically the same because you have two clusters in the calorimeter and also the two tracks in the silicon vertex tracker. But also a bit more fancier process, which is called Bethe-Heitler, that results basically in the same final state. So 3 electrons that may impinge on your calorimeter. But there is a difference between these two, because if you look at the distribution of the energy of electron and positron produced by these two processes, so in this case and in this case, you can see that while the radiative process is distributed, obviously they took almost all the energy of the beam, because this is a sort of Bremsstrahlung, as in the case of the dark photon production. This is very similar to what you expect from the signal, so it's not, it cannot be reduced, while this one results in lower energy electron-positron pairs, which are distributed here, and therefore we are more able to reject this kind of event in analysis, during the analysis. Okay, so what's the status of HPS? HPS is basically has performed a sort of commissioning with several engineering runs, which are used to optimize all the parameters of the experiment. And they performed a final engineering run in 2016, and they published some first limit obtained from the bump-hunt search. So here you have the obtained invariant mass spectrum in this search. They search for bump-hunt, for bumps, peaks, we did not find them. And here, instead, you have the result of the displaced vertex search. Here on the X you have invariant mass, and here the vertex which is measured. Here you have the background, basically, and here is your approximated signal window. But for this statistic, it was not enough to set limits using this technology, this technique of displaced vertex. So we set limits only using the bump-hunt. And these are the result. This was just an engineering run, so not really data taking complete data taking from the experiment. And they were able to place this limit here, which, being a search for a bump-hunt, so a peak in invariant mass, is similar to the shape of the searches which I described before, for example, for the colliders. And this instead is the projection for the displaced self vertex as soon as HPS will be able to collect the statistics that has been defined by the collaboration. And you can see that using a technique which is similar to what LHCbC did for the displaced vertex, so searching for displaced search vertex, the explorable regional parameter space is closed. And it is very interesting because it is just in the middle of it, which is the thermal target, so the regional parameter space that could explain dark matter in the hypothesis of thermal origin of dark matter. So this was all for HPS. Now we'll change a bit physics scenario, because I want to talk to you for a few minutes about an experiment, which is a nuclear physics experiment, which you may think does anything to do with does not have anything to do with dark matter, but that's not the case. So I want to talk to you about the atom key experiment, which is an experiment in Hungary, and the aim of this experiment is to study the angular correlation between electron and positron pairs produced by internal pair conversion in the de-excitation of excited beryllium-8 nuclei. So what it is, all this weird thing, I will discuss it. So what they did is to have a lithium target, sorry. They made a proton beam with order 1 MeV mass energy impinge on this target. And from this reaction of impinging, of talking of very small energy, with really nuclear physics, so very small if compared to what we were talking before, they excite a state of a beryllium-8. So like the proton is capturing, is being captured by the lithium, you have the beryllium produced in excited state, which is to say it has to de-excite to go to the standard beryllium state we know, and this is stable. beryllium-8. So then what happens is from the de-excitation of these excited states, two electrons, an electron and positrons are produced, and in this experiment they want to measure the energy as the angle and the angle of emission of these particles. So this is due for nuclear physics reasons, so I won't go into detail here. But they have a detector surrounding the target, which is made of plastic scintillator, and again some kind of trackings, which in this case is a bit different, but again what does it to measure the impinging position of the particle. And so when you have an electron and positron exiting from your target, you can measure both their angle of emission and their energy. So here a bit more in detail, these are the states, the excited states of beryllium-8. So the states that they can produce with this very low energy proton beam impinging of this lithium target. And so you produce two excited states depending on the energy of the beam you use. You can go 1 MeV or 0.4 MeV, and you produce two different excited states of these nuclei, and then they decay to the ground state of beryllium-8. Here is the cross-section for this reaction of the proton beam impinging on this lithium target, which has a spike in correspondence of the two energy used to excite this level. So why I'm talking about this? Because while we were searching for other things, we were studying the angular distribution of these two emitted electron and positron. They plotted the opening angle of the electron and positron, and they saw a weird bump feature, which we were not expecting, because in this kind of nuclear reaction, you expect to have a very flat distribution. So what we did as soon as they saw this weird feature is to try to think if this could have been explained introducing a new particle which decays in a couple pair of electron and positron, which can give rise to this bump here. So the picture that they imagined is this one. So you have the proton beam impinging on beryllium target, you excite the beryllium-8 state, then from the de-excitation, instead of producing a photon, you produce some resonance, some new particles, which then decay to electron and positron pair. So here the idea is very simple. They thought, well, this is coupled to photons, is coupled to electrons and positrons, this is maybe a dark photon. So they thought we discovered dark photon. We did not say we discovered dark photon, but they published a paper where they saw possible evidence of a new particles decaying to electron and positron pair. And given the fact that they know the energy of this excited state and they measure the energy of the electron and positron pair, they know quite reasonably the mass of these hypothetical particles. So at first glance, really no one cared about this result because they consider some nuclear physics weird thing, and it's still possible that this bump here is due to nuclear physics effect, which has not been studied yet. But they went on and performed other measurements using also other nuclei and changing also the detector. And they kept seeing this weird shape in the opening angle distribution of the particles. So they performed an experiment with a new detector. This is the photograph of the new one with this detector here with the plastic scintillator and the tracking detector to detect the position of the impinging of electron and positron. And here is the comparison between the plots obtained for the angular distribution with the old new setup, which is really consistent. And they went on and they performed the same measurement with an excited helium nuclei, and they also obtained the same signature. I think they did also with carbon, and they published in the last period. So again, this is something we don't know what it is. It may be just some nuclear artifacts, some artifacts due to their analysis, to their detectors, but still the interest in this thing is raising a bit. It's raising a bit because if you look at the region of a parameter space that in terms of dark photon candidate could explain that bump in the angular distribution, so via atomic collaboration, this is a region where there's still some parameter space free and free to explore. And this parameter space, you see the zoom, is very difficult to explore because you have a particle that still you can produce a reasonable way because you're not in the very low region, in the low region for the epsilon coupling, but it's still very short-lived. So it's complicated. It's a region which is a boundary between the collider, fixed target experiment, thin target, and as we will see, bin dumps. So something that has raised some interest in the community, and since I have no time, we will see tomorrow that there is one experiment which has been designed really on the fly. I have to say it's an old experiment that is being converted to this search to try to see if this is really a new particle, so searching it from the point of view of particle physics and not nuclear physics, or if it's just another illusion from the point of view of dark matter. So I think that I can stop here since I have 1 minute, and we will see the rest tomorrow.
Thanks, Luca. So I think we can jump to the general questions, yeah, and for all the speakers, but of course, Luca. So, yeah, I see Danielle here. Javier is there. Oh, there's Maria.
Thank you for your talk. I am not sure who would answer my question, but if a direct detection experiment sees a signal that could be dark matter, how would the accelerator experiments react to it? Like, is there a way to probe like specific, like the probable mass or something like that?
Well, as it was said yesterday by Javier, you really need a model to make comparison. So if you don't make a model, it's impossible to make the two worlds to speak to each other. So for example, if you see a signal in an experiment which is searching for WIMPs, and therefore it has a sensitivity that can explore some region in the WIMP parameter space, you will probably be reasonably sure that the discovered particle has mass larger than something. So you may try to search it, for example, at colliders when you can achieve that large energy. On the other side, it would be complicated to the opposite. One important thing to remember about the searches at collider and accelerator is that you search for candidates, not for dark matter. So if you see a signal, for example, for this, let's say that tomorrow we discover this new particle, which is the dark photon, you probably have discovered only a new mediator, but you don't know this is the portal to dark matter, if it's a portal to a dark sector of particle which is not dark matter because it's not making the 85% of the mass of the universe, and so on. So it's really model dependent, and I think that at the end of the day, while colliders can give, what can I say, can explore these theories and find something new, so beyond the standard model, still you will not be sure that it's dark matter. And on the other side, we need to have the answer from direct search. So this is the reason why it's important that the research to go down in mass, for example, go on in direct searches, and so on.
Thank you.
Do you want to complement this, Daniel? Or no? No? As you wish.
No, I mean, I think that is the right answer. If you have a new light dark matter particle with some new mediator, I mean, you do want to separate out the dark matter particle and the mediator itself. So accelerator experiments will be important for disentangling those two effects, so that you sort of have some idea of where to take, in which directions the next accelerator facilities and collider experiments and beamed up facilities. But yeah, I think Luca basically covered it right.
Since I have the microphone, I would like to ask a question to Dan. So you had a plot where you have shown these two regions of interest. So you had time in the x-axis and like detection in PMT.
Yeah, for the waveform for the CSI-7s.
For sevens in coherent, yes. So that plot is like it's for each pulse. For each pulse, you can check at the arrival time of the signal and do a plot like that.
Yeah, that's absolutely right. And there are some pulses from just background scintillation in the crystal, basically just afterglow, long-lived scintillation lifetimes. So that's a thing that you'll always have to deal with. If you see an actual physics event, which can happen anywhere in your waveform, you'll basically see a cluster of pulses, and you'll reconstruct that cluster by finding the first pulse in the cluster. And depending on where that is, that basically reconstruct your timing, decides on whether the event lives in your coincidence ROI for measuring the neutrino interactions, or the anti-coincidence for getting the background.
Thanks. So you have like a connection to the beam itself, or you know exactly.
Absolutely. Yeah, we have a little pulse coming in from the beam saying like this is when the protons were supposed to be in the target, and then about a microsecond later is like, yes, we actually did put some protons on that target. Yeah.
Thanks.
This is like an open question. It's more out of curiosity, like when you are colliding the beams, so you are taking data, and for how long? And even though this is a collimated beam and everything, does it kind of not bend but shift a bit during the data taking? And if so, when do you decide like to stop the data taking to again put it both beams again in shift?
You mean you were speaking about HPS or collider?
The collider.
The collider. So the collider actually are controlled to a very fine level. I have my experiences on CERN, and basically you have a very incredible level of control of the impact position of the two beams. You have to imagine, and this is not very intuitive, but let me see if can I go back to the slide. There was an aerial picture of CERN, but so actually, what happens when CERN is operated, when LHC is operated, sorry, is that you have the protons that goes inside the collider in the two directions, that are provided by a smaller accelerator, which is as you can see here, this small ring here, which is called SPS, super proton synchrotron, and the protons to the super proton synchrotron comes from another smaller accelerator. So what happens is that at some point during the day when you are taking data at LHC, there is the so-called filling. So you put particles from the SPS to the LHC, and this lasts about half an hour, okay? And then the LHC is filled with protons to its max level, as you can say, and then they make the collision to start by changing the magnets, okay? So until the beam is degraded, so these collisions go on and go on, also maybe collision with the pipes itself, they degrade it, they go on without any other filling. So they have the same protons turning and turning again inside the collider. And this last, the record I think was a few days. So they can go on. They're so precise in bending the beam and making it follow the trajectory of the accelerator that can go on for several hours without having to refill this ring with protons. So I think I can answer that the control is very high level, and you decide to stop and to make another fill simply when you don't have any more particles, or the number of particles goes below such a level that it's not more convenient to go on, because the number of interaction decreases up to the level when it's better to do a refill. So you activate the SPS. Actually, SPS works on its own for other experiments, as we will see. But you ask the SPS to provide another filling of protons, for LHC.
Okay, thank you.
Okay. I think I will go first, or he go first. Okay, sorry. So, Javier showed us a plot where, like, the experiments using xenon are start to increase, and you mentioned that we will have a point that we are going to use like 1/3 of the accessible xenon in the world, right? And do you know if about like the same statistics for argon, for example? I know that Dune is going to use a lot of argon, and we have a lot of argon experiment as well. So do you know like how much argon left?
Yeah, for argon, it's not a big problem, because argon is used, well, first of all, it's a lot easier to get argon. So if you are just going to use argon for industrial applications, you get it from the atmosphere. So you don't need to mine it. It's a lot easier to get and a lot cheaper, and it's very, very abundant around us. Also, there are a lot of industrial applications that use argon, so the production scale is huge. I mean, for welding and for many processes that require, I mean, environments that do not react, argon is used. So it's not going to be a problem. What is a lot more difficult is to get argon without this radioactive isotope that is argon-39. And essentially, well, the only user for that is dark matter searches. So all that argon is coming from these very few sources. So essentially all the argon that is depleted in argon-39 is being used by the dark matter community. For Dune, I mean, it depends on which of the analysis and projects within Dune you are considering, but you don't need this highly depleted argon because you have the beam signal there, so you don't need especially very, very low background for most of the analysis. So it's not going to be a problem for that, but yes, for the dark matter searches in which you really need this argon that is depleted, then it's 100% of the production, and even new facilities are being built to produce more of this depleted argon or to separate isotopically the radioactive component. And so that, I mean, there is a distillation column that is being project in Italy that is huge. It's 100 meters or more of distillation column just to be able to skim this radioactive component. Yeah.
Okay, thank you.
About that experiment of using beryllium, that 17 megaelectrovolt emission is something special about beryllium. Didn't anyone try using other atom, or the emission is something that we expect from beryllium, but no other experiment?
They were studying beryllium from other purposes other than dark matter, and so they discovered, I mean, they observed this anomaly first on beryllium, but yeah, they did it also the test on other nuclei. So they did it on helium and I think on carbon now. So and also they saw it on a coherent nuclear resonance, which is I mean, I won't explain here, but so we're going on with our studies on this effect, on this anomaly, and it is an interesting puzzle. I mean, even if not from the point of view of dark matter, if you don't believe that it is reasonable that it's dark matter, it's something that is interesting to study. I think that, as we will see tomorrow, having an experiment or few experiments that exclude the possibility that is a dark photon or something similar from the point of view of particle physics and not point of view of nuclear physics, where you have a lot of uncertainties due to the processes that really you don't know at a higher level what happens within the nucleus. So it's really something that has to be, I think, has to be done, interesting to be done, and for sure it will be done in the next few years. But yeah, it has been done already in other nuclei.
Okay, thank you.
More questions?
Thank you. So this is a question for both Javier and Daniel. We have heard about the neutrino fog or floor as a kind of bad thing, but isn't it a good opportunity to study neutrino physics?
Yeah, for sure. I mean, someone's background is someone else's signal, so yes.
Yeah. I mean, I study sevens. I very much like the physics connected with it. One of the things that you really want to understand is, you know, is the sevens cross-section the same for all flavors? That connects up with all sorts of NSI scenarios. The typical way to study sevens with man-made sources is with reactors and PIDAR beams. That gives you nu-e bar and nu-mu/nu-e/nu-mu bar you're missing new taus out of the picture entirely, which are in the solar neutrino flux. So this is just a brilliant opportunity for Xenon, NTON, and PendaX, which released this morning. Some observation of the 7 signal coming from solar neutrinos is actually going to do very complementary measurements and constraints compared to the man-made sources that we have. So yes, the information coming out of the dark matter experiments is very interesting for us as neutrino physicists.
Okay.
Yep.
Thank you. So I actually have another question for Luca now, if I may. But this one is for Luca. So about the atom key experiment, so has it been cross-checked, or is it too hard to cross-check? Do you know?
Well, it is not yet being cross-checked. There are several efforts going on. There are few, I say, human issues going on that side, because what happens in these cases is that maybe repeating the measurement requires a lot of effort. So you have to have money, manpower, and decide that you have to give your time to this search. And yet, at the end of the day, if you do it and you see the same thing, you will only be the second one to have seen the same thing. So repeating the measurement in another way, so with our accelerator, for example, to not repeating the measurement, but exploring the parameter space of that resonance, if it's a resonance, is a different thing, because it's another measurement, and there is some effort in that direction. There is an effort also in the direction of repeating the same exact measurement, maybe with some different detector. But I think this is going a bit more slowly. I know there is an effort in Italy, for example, but also this, at least I can speak from what happens in Italy, this is a nuclear physics technology, so low energy technology. And the outcome is not a nuclear physics outcome. It's another sector of physics, which is dark matter, beyond standard model. What happens often is that laboratories that do nuclear physics, they want to stick to do nuclear physics. They have their own program. Maybe they don't believe this thing. They just think it's some... I think that is similar somehow, not similar, it's different case, but there is some, how can I say, human component, as in the case of Dama. So from it will be reasonable to repeat things, to be open about things, to go on and to solve these doubts and to understand, but there are some human components that maybe slow the process, even if I'm sure that sooner or later it will be redone. Also because it's not a really complicated experiment, but still these people at Atomkey, they do it. I mean, having done this from years, they know how to do it. So it's really a matter of precise know-how. I've been involved a little in this effort in Italy that I was mentioning, and I know that is no joke. I mean, you have to really, you need some effort, human effort and money to do it. So it will be done, but with the right time scale.
Thank you.
Thank you for the lectures. Just was wondering in the search for the dark photon, if has been considered another channels such quantum like a scattering, photon, electron going to dark photon, electron. I don't know if it is constrained for some reason or.
I don't understand the channel you are mentioning. So you said are decay channels, or I don't?
No, photon and electron. Going to dark photon and electron to the final state.
Photon, electron.
Going to dark photon, electron.
Going to dark photon, electron. That is not available, not permitted, I think.
Why?
If I understood. Because you mentioned a vertex where you have an electron, a photon, and a dark photon. right?
Dark photon and the final state with electron.
But then the dark photon is an internal line.
Now the dark photon is in the final state because you can actually measure the using the missing energy technique.
Okay.
I think, for example, you can put like a calorimeter or something and see how is the final state of the electron or.
Okay, we will talk about missing energy for sure the last day, and maybe we can discuss with this with a piece of paper, which is which is better. You can show me what you mean. For
It's like a scattering. Yeah.
Ah, okay. So sorry, I don't understand. Yeah, but I mean, from the point of view of missing energy, is much better to use the radiation processes like that, because the high energy that you are considering, the dominant, we see that it's not the only one, but one of the dominant production channel is the radiative one. So even for a missing energy experiment, which we will see an A64, for example, relies on that process.
Okay, thank you.
My question is regarding the alpha decoupling. Is there any running? I mean, through the randomization scale?
So you mean if there are bounds on the alpha D on the normalization scale? So this is so the variation in the alpha D parameter. So I don't even see you, so don't know what from the. Ah, sorry. Okay. But can you hear me, right? Yeah. So you mentioned. Can you hear me now? For maybe it was. Okay. So you mentioned if there is running of the alpha D constant from a renormalization scale. Yeah, probably, yeah. But I mean, I want to stress that. I mean, from the point of view of phenomenology at this energy scale, really the important thing is you see, for example, the scenario that I show fix the value to alpha of, for example, to 0, 1, okay? But this is just an arbitrary choice. There are some limits, I think, from cosmology, for example, but this is just the important thing for all the phenomena from the point of view accelerator is that you have two couplings, standard model dark matter, which is epsilon, and alpha dark, which is inside the dark sector, and one is much smaller than the other. So this basically limitates and defines the phenomenology on a reasonable level. Then, yeah, for sure there is running for dark too, but you can think of many more. This is just a toy model. You can think of many more complex thing. We wonder where does the mass of chi particles come from? If there is a dark sector, a dark Higgs mechanism, all whatever you want. So that's it.
So we have time for one last question.
So while people think about the last question, just announcement or comment. If you didn't sign up the sheet, okay, great. If someone didn't sign up the sheet yet, please do so before leaving the room, after we get rid of it. So don't forget. And yes, today, just a reminder, we start at 2:30, all the activities. For USP, meet us at the stairs, and all the rest that stay here, just go 2:30. But yes, we can ask one question still.
Okay, no question. So let's thanks the speakers again.